Bolted fault current, often referenced in the context of electrical safety and arc flash hazard calculations, is a critical concept for electrical engineers and technicians to understand. The Institute of Electrical and Electronics Engineers Standard 1580 Formulas 2002, titled IEEE Guide for Performing Arc Flash Hazard Calculations, provides a definition that clarifies its meaning. Bolted fault current, denoted as F, is the maximum fault current that can flow through a circuit when a fault occurs at the point of calculation. In simpler terms, it represents the highest possible current that the electrical system is capable of delivering under short-circuit conditions at a specific location. The term bolted fault current is synonymous with maximum available fault current, highlighting that it's the upper limit of current that the system can supply to a fault. Several factors influence the magnitude of bolted fault current. These include the source impedance, which is the opposition to current flow offered by the power source such as a transformer or generator, the impedance of the conductors in the circuit, and the voltage level of the system. Understanding these factors is crucial for accurately calculating the bolted fault current at any point in the electrical system. Calculations typically involve complex formulas that take into account these impedances and the system voltage. Software tools are often used to simplify the calculations, especially for complex electrical networks. Knowing the bolted fault current is essential for several reasons. Firstly, it's a primary input for arc flash hazard calculations. The bolted fault current, along with the clearing time of the overcurrent protective device, determines the incident energy of a potential arc flash event. Incident energy is the amount of heat energy a worker could be exposed to during an arc flash, directly impacting the severity of potential injuries. Secondly, the bolted fault current is used to select appropriate overcurrent protective devices such as circuit breakers and fuses. These devices must be able to interrupt the maximum available fault current to prevent equipment damage and ensure personnel safety. The interrupting rating of the protective device must be greater than the calculated bolted fault current at its location. Thirdly, bolted fault current calculations are vital for equipment selection. Electrical equipment, such as switchgear, panel boards, and transformers, must have a short-circuit current rating that exceeds the calculated bolted fault current at their respective locations. This ensures that the equipment can withstand the stresses imposed by a short-circuit event without failure. Failure to properly coordinate the interrupting rating of overcurrent protection and the short-circuit current rating of equipment can result in catastrophic equipment failure and potentially life-threatening hazards. Let's delve deeper into how to calculate bolted fault current. The calculation method varies depending on the complexity of the electrical system and the available information. However, the basic principle involves determining the total impedance of the circuit from the source to the point of the fault. The formula for calculating bolted fault current is generally expressed as follows: F equals volts divided by Z, where F is the bolted fault current, volts is the voltage at the point of the fault, and Z is the total impedance of the circuit. The impedance Z includes both resistance and reactance. Resistance is the opposition to current flow due to the conductors and other circuit elements. Reactance is the opposition to current flow due to inductance and capacitance in the circuit. In most power systems, inductive reactance is the dominant factor. To accurately determine the total impedance, one must consider the impedance of the utility source, transformers, conductors, and any other components in the circuit. Utility source impedance is typically provided by the utility company. Transformer impedance is usually found on the transformer nameplate and is expressed as a percentage. Conductor impedance can be calculated based on the conductor size, material, length, and insulation method. Once all the individual impedances are known, they must be combined to find the total impedance. This involves using complex number arithmetic, as impedance has both magnitude and phase angle. After calculating the total impedance, the bolted fault current can be determined using the formula F equals volts divided by Z. The voltage used in the calculation should be the nominal voltage at the point of the fault. This calculation provides the symmetrical bolted fault current. However, the actual fault current may be asymmetrical due to the DC offset component. The asymmetrical fault current is higher than the symmetrical fault current and is used for specific applications, such as calculating the mechanical forces on bus bars. Now let's consider some practical examples. Firstly, imagine a scenario in an industrial plant where a 480 volts motor control center is fed from a 1500 kilovolt ampere transformer with a 5.75% impedance. To calculate the bolted fault current at the motor control center, we would need to know the utility source impedance, the transformer impedance, and the conductor impedance between the transformer and the motor control center. Assuming the utility source impedance is negligible and the conductor impedance is relatively small, the transformer impedance will be the dominant factor. Using the transformer impedance, we can calculate the bolted fault current. The transformer impedance is 5.75% on a 1500 kilovolt ampere base. We first need to convert this to an ohms value. The base impedance is calculated as volt squared divided by volt amperes, which equals 480 volt squared divided by 1,500,000 volt amperes equals 0.1536 ohms. The transformer impedance in ohms is then 0.575 multiplied by 0.1536 ohms equals 0.8832 ohms. The bolted fault current is then calculated as 480 volts divided by 0.8832 ohms equals 54,348 amps. This is a simplified calculation, and a more detailed analysis would consider the utility source impedance and conductor impedance for increased accuracy. Secondly, let's consider a commercial building with a 208 volts panel board fed from a 75 kilovolt ampere transformer with a 4% impedance. Similar to the previous example, we need to determine the transformer impedance, conductor impedance, and utility source impedance. Assuming the utility source impedance is negligible, we focus on the transformer and conductor impedance. The base impedance is calculated as volts squared divided by volt amperes, which equals 208 volts squared divided by 75,000 volt amperes equals 0.5765 ohms. The transformer impedance in ohms is then 0.4 multiplied by 0.5765 ohms equals 0.2306 ohms. Let's also assume the conductor impedance is 0.1 ohms. The total impedance is then 0.2306 ohms plus 0.1 ohms equals 0.3306 ohms. The bolted fault current is then calculated as 208 volts divided by 0.3306 ohms equals 6,291 amps. This calculation provides an estimate of the maximum available fault current at the panel board. Understanding the implications of bolted fault current is crucial for electrical safety. High fault currents can cause significant damage to equipment, create arc flash hazards, and pose serious risks to personnel. Arc flash is a dangerous phenomenon that occurs when a short circuit creates a high-energy explosion. The heat from an arc flash can reach temperatures of up to 35,000 degrees Fahrenheit, causing severe burns, blindness, and even death. The incident energy of an arc flash is directly proportional to the magnitude of the fault current and the clearing time of the overcurrent protective device. Therefore, accurately calculating the bolted fault current and selecting appropriate overcurrent protection are essential for mitigating arc flash hazards. To protect workers from arc flash hazards, employers must implement appropriate safety measures. These measures include conducting arc flash hazard analyses, providing personal protective equipment, establishing safe work practices, and training employees on arc flash safety. Personal protective equipment, or PPE, includes flame-resistant clothing, gloves, face shields, and helmets. The level of protection required depends on the calculated incident energy. Safe work practices include energizing equipment before working on it, using insulated tools, and maintaining safe distances from energized parts. Training employees on arc flash safety is crucial for ensuring they understand the hazards and how to protect themselves. Regular refresher training is also essential to reinforce safe work practices. In addition to protecting personnel, understanding bolted fault current is also important for protecting equipment. High fault currents can damage conductors, transformers, switchgear, and other electrical equipment. To prevent equipment damage, it is essential to select equipment with a short circuit current rating that exceeds the calculated bolted fault current at its location. This ensures that the equipment can withstand the stresses imposed by a short circuit event without failure. Overcurrent protective devices also play a critical role in protecting equipment. These devices are designed to interrupt the flow of current during a short circuit or overload condition. The interrupting rating of the protective device must be greater than the calculated bolted fault current at its location. If the interrupting rating is too low, the protective device may fail to interrupt the fault current, leading to equipment damage and potential hazards. Proper coordination of overcurrent protective devices is also essential for equipment protection. Coordination involves selecting and setting the protective devices so that the device closest to the fault will operate first, minimizing the impact of the fault on the rest of the electrical system. This helps to prevent unnecessary outages and protect equipment from damage. Standards such as the National Electrical Code, or NEC, and NFPA 70E provide guidance on selecting and coordinating overcurrent protective devices. The NEC contains requirements for the interrupting rating of overcurrent protective devices, while NFPA 70E provides guidance on arc flash hazard assessments and safety-related work practices. Compliance with these standards is essential for ensuring electrical safety and protecting both personnel and equipment. Bolted fault current calculations are not a one-time task. The electrical system should be re-evaluated whenever there are changes, such as the addition of new equipment, modifications to the distribution system, or changes in the utility source impedance. These changes can affect the bolted fault current and may require adjustments to overcurrent protection and equipment selection. Regular maintenance of electrical equipment is also important for ensuring its continued reliability and safety. Maintenance activities include inspecting and testing overcurrent protective devices, tightening connections, and cleaning equipment. Neglecting maintenance can lead to equipment failures and increase the risk of electrical hazards. Bolted fault current calculations are used to determine the appropriate short-circuit current ratings for electrical equipment. Firstly, switchgear and switchboards must have a short-circuit current rating that is equal to or greater than the calculated bolted fault current at its point of connection. This ensures that the switchgear and switchboard can withstand the mechanical and thermal stresses of a short-circuit event. Secondly, panel boards must also have a short-circuit current rating that is equal to or greater than the calculated bolted fault current at their point of connection. The panel board short-circuit current rating is based on the lowest rated component within the panel board, such as the main breaker or branch breakers. Thirdly, transformers must have a short-circuit withstand rating that is equal to or greater than the calculated bolted fault current at their secondary terminals. This rating is based on the transformer's impedance and its ability to withstand the mechanical forces generated by a short circuit. Fourthly, conductors must have an ampacity that is sufficient to carry the calculated bolted fault current for the duration of the fault. The NEC provides tables that specify the allowable ampacity of conductors based on their size, insulation type, and insulation method. Fifthly, motor control centers, or MCCs, must have a short-circuit current rating that is equal to or greater than the calculated bolted fault current at their point of connection. The MCC short-circuit current rating is based on the lowest rated component within the MCC, such as the busbars, starters, or circuit breakers. Bolted fault current is also relevant for selective coordination of overcurrent protection. Selective coordination is a design practice that ensures that only the overcurrent device closest to a fault will operate, minimizing the impact on the rest of the electrical system. To achieve selective coordination, the interrupting time current characteristics of the overcurrent devices must be carefully coordinated. The upstream devices must have a longer clearing time than the downstream devices, so that the downstream device will clear the fault before the upstream device operates. Bolted fault current calculations are essential for determining the appropriate settings for the overcurrent devices to achieve selective coordination. Voltage fault current is also vital for arc flash hazard analysis. Arc flash hazard analysis is a process of evaluating the potential arc flash hazards in an electrical system. The analysis involves calculating the incident energy, arc flash boundary, and personal protective equipment requirements for each piece of equipment in the system. The voltage fault current is a key input for the incident energy calculation. The incident energy is the amount of thermal energy that a worker could be exposed to during an arc flash event. The arc flash boundary is the distance from the arc flash source at which the incident energy is equal to 1.2 calories per square centimeter, which is the threshold for second-degree burn. Voltage fault current calculations are essential for complying with safety regulations. OSHA, or the Occupational Safety and Health Administration, requires employers to protect employees from electrical hazards, including arc flash hazards. Compliance with NFPA 70E is often used to demonstrate compliance with OSHA regulations. NFPA 70E requires employers to conduct arc flash hazard analyses, provide personal protective equipment, and train employees on arc flash safety. Voltage fault current calculations are an essential part of complying with these requirements. Software tools are available to assist with voltage fault current calculations and arc flash hazard analyses. These tools can simplify the calculations and provide detailed reports on the potential hazards in the electrical system. Some popular software tools include EasyPower, SKM Power Tools, and NetApp. These tools can also be used to perform coordination studies, load flow studies, and other power system analyses. Voltage fault current calculations can also be used to improve power system reliability. By accurately calculating the voltage fault current and selecting appropriate overcurrent protection, it is possible to minimize the impact of faults on the electrical system. This can help to prevent unnecessary outages and improve the overall reliability of the power system. Voltage fault current is an important parameter that should be considered during the design, installation, and maintenance of electrical systems. By understanding the concept of voltage fault current and following the recommendations of standards such as IEEE and NFPA 70E, it is possible to create safer and more reliable electrical systems. Remember to always consult with qualified electrical engineers and technicians for complex calculations and system designs.